a differential equation is an equation of the form, well, first order differential equation is an equation of the form y prime equals some expression of t and y. But this expression of t and y, depending on the particular values of t and y, it may or may not be defined, right? And the set of all pairs ty such that the right-hand side is well defined is called the domain of the differential equation, or the domain of the right-hand side of the differential equation. So let's go through a few examples of the domain of the right-hand side of the differential equation. So here, the right-hand side has a square root, and for a square root to be defined, the expression inside the square root has to be non-negative, right? So in our case, it means that t squared plus y squared is greater than or equal to 4. And, well, I hope you still remember that the equation t squared plus y squared exactly equals 4 is the equation of a circle centered at 0 of radius 2. So if it is greater than or equal to 4, this is the exterior of the circle, right? So which means that our expression is not defined whenever t squared plus y squared is less than 4. Well, and then if you plot the corresponding direction field, then it means that inside the circle you're not going to see anything. So here, the right-hand side is simply undefined. It's not available. Right, so the domain is the set of all points where it is well defined, so which is the exterior, so whatever it's is not inside the circle. Okay, here is another differential equation. So here we have the right-hand side contains ln, and in order for ln to be defined, the argument of ln has to be exactly positive. Right? So here, 1.5 minus absolute value of t plus 1 has to be positive. But then you can solve this, so absolute value of t plus 1 is less than 1.5. Or t plus 1 itself is less than 1.5 and bigger than negative 1.5. So t is between minus 2.5 and 0.5, and this is what you see. So there are only arrows here corresponding to the values of t between minus 2.5 and 0.5, and the domain of the right hand side looks like an infinite vertical strip. So here is a combination. So here the argument of ln has to be strictly positive, and the argument of square root has to be non-negative. But then if you solve these two inequalities together, then you will see that the domain of the right-hand side of this differential equation is a square. But it's a bit tricky, right? So when t is negative 2 or positive 2, so these points are not included in the domain. So here it is undefined. But when y is negative 2 or positive 2, so here it is actually well defined. These two parts, the right hand side is well defined. So the domain of the right hand side here is, well, it is a square, but it's a bit open on sides and closed on top and bottom. Well, and here's a challenge for you. So can you think of a specific expression so that the domain of the right hand side of the corresponding differential equation is something like this? So two disjoint union of two disks. Well, as you see, I have solved it myself, and I plotted this picture. So the challenge for you is to figure out how I did that. So again, in the next example, the right hand side is t over 3y, and again, so the domain is of the right hand side is whatever combinations of t and y for which the right hand side is well defined. So in other words, when you need to determine the domain, you need to think is it possible for certain values of t and y that the right-hand side is undefined, right? And if you have ln, then the argument of ln has to be positive. So if it's negative or 0, then it's undefined. If you have square root or fourth root, anyway, so any fractional power where the exponent has even denominator, then the argument should be non-negative. Well, but here there is no ln, but there is division, right? And whenever you have a division, the numerator, there is no problem with the numerator, but denominator cannot be 0. So which means, in this case, it means that y cannot be 0. And again, we can see this due to absence of arrows along the line y equals 0. Well, sometimes when we apply differential equations to model something in real life, then sometimes it makes sense to restrict the domain of the differential equation artificially. So it's like if you try to model the population, then although mathematically, if you just write this differential equation, then of course it is defined for all values of y, positive and negative, but since population has to be negative, then it may make sense to just artificially restrict the domain, right? So in other words, when you introduce this differential equation, you just add the condition that y is bigger than or equal to 0. Okay, I hope this is clear, and here is a little quiz for you. So please, I suggest that you pause